is on inequalities. As usual, we have a video guide to go along with this video. If you haven't already printed the video guide, go ahead and pause the video, print it, come back, and then work out the examples with me. So we're talking about inequalities today. We've done equations and solving equations and looking at equations, working with them for a while. Remember, equations must be equal to each other. We have the equal sign, and it means the two sides are the exact same amount. Okay, inequalities are different from equations, so we need to go ahead and define the word inequality so that we're ready to actually work with the different symbols that we'll be using instead of the equal sign. So an inequality is a relationship between two values. And that relationship, again, this is different from an equation because an equation is also a relationship between two values, but it's always equal. So an inequality is a relationship between two values that exceeds or goes beyond equality. So they're not just equal anymore, okay? The two amounts do not have to be exactly the same, and it depends on which sign you are given that will determine whether or not it's bigger or it's smaller and so forth, and we need to talk about that terminology. So it exceeds equality, and we're going to dive into that a little bit more right now so that we understand what that exactly means. Now I've got four different symbols up here, and many of you have probably already seen them before, but let's make sure that we remember which one's which. This symbol, okay, that opens up to the left is called greater than. Okay, this is the greater than symbol, or another way of thinking about it is bigger. This is the bigger symbol, okay? So it's telling you whatever you have on the left side is bigger than whatever's on the right side. So I could have the example 5 is bigger than or greater than 3, which is a true statement. 5 is bigger than 3. This is an inequality. They're not equal to each other, but it shows a relationship still. Okay, so it's telling me about the relationship that goes beyond just equality, all right? Because not everything in life is equal. So this gives me more symbols that I can use to help me show the relationship between two amounts that are not necessarily equal. Now, the nice thing about inequalities is they can also represent equality. All right, so this is a greater than symbol. This one opens the same direction, okay? The Y part is opening up to the left. It's still the greater than symbol, but there's more to it. It's greater than or equal to. So it could be either one, all right? Which this bar underneath is what tells us that it's equal to. So it's greater than or equal to. For example, we could still use the 5 is greater than or equal to 3. This is a true statement because it either has to be bigger or it has to be equal to. In this case, 5 is bigger than 3. The statement is still true though, okay? Because it can be either or. It won't be both. I could also write this as 5 is greater than or equal to 5. Okay, this statement is also true. It's saying it's bigger than or it's equal. All right, in this case it's equal, in this case it's bigger than. Both are true, so this is another way that we can write it, okay, using that equal to bar. So that's greater than. Now our opening is going off to the right side, okay, so it's changed, which if it's going the opposite direction, it would make sense if it meant the opposite, which it does. If this is greater than, this is less than. Or another way to say that is smaller. So it's saying the amount on the left is smaller than the amount on the right. So to use different numbers, we could say that 2 is smaller than 9. And that's a true statement. Again, it's another way of showing a relationship when equality doesn't work. I couldn't say 2 equals 9 because it doesn't. But I can say 2 is less than 9 and use that symbol instead of writing it out as a sentence. So inequalities helps us show relationships that are not equal. So 2 is less than 9. All right? And then this one, you'll notice, there's that equal to bar again. So this is the less than or equal to. Okay? So it could be either or. All right? It could be less than or it could be equal to. So we could use our numbers from before and say 2 is less than or equal to 9. That is a true statement. Okay? It doesn't have to be both. All right? It doesn't have to be less than and equal to at the same time because it can't be. That's not possible. But it's giving you the option. It can be less than or it could be equal to, either one. We could also write 2 is less than or equal to 2, which is a true statement. 2 is equal to 2. It has to be either smaller or equal to. And in this case it's equal, in this case it's smaller. Okay? But it's always the relationship of left to right. The left side is bigger than the right, or the left side is smaller than the right. Just like you would read a sentence from left to right, you read these inequalities from left to right. So the relationship is the left is smaller than the right, or the left is bigger than or equal to the right, okay? Depending on which symbol you have. All right, I also think of it as the inequality is always eating the bigger part. All right, I don't know, some of you might have heard the crocodile with teeth. He's gonna eat, a crocodile is pretty hungry, he's gonna eat the bigger amount, all right? So if he's eating the 5, that means the 5 is bigger than the 3. All right, or here, if he's eating the 9, because 9 is the bigger number, 2 is smaller than the 9, because the crocodile is going to eat the 9, okay? Now, real quick, the reasoning why we go over inequalities is because, honestly, that's more of what we're used to in real life. Equations and stuff is great as far as when you're totaling up a bill, things like that. But if you think about when you first walk into that store, let's say I have $20 in my pocket and I go to Target, all right? I'm not going to say, well, I have $20, so I have to spend $20 at Target. That's not true at all. The amount of money I have, if we call it X, if I have, that's how much I want to spend is X, and I have $20 in my pocket, I would use an inequality to show the relationship between what I can spend and what I have. So if I have $20 in my pocket, I can't possibly buy something that costs $30. I don't have enough money. I left my credit cards at home, all I've got is my $20. I have to spend just $20 at the most. I could spend $5. If all I found was something that cost $5, that would be fine, but I can't go over the 20. So that means an inequality would be appropriate here. If I said, well, I have to spend the 20 because that's what I have in my pocket, that's not true, okay? And most of us don't do that. And usually our total does not come out to be a perfect 20 when we go up to the cash register. But I can use an inequality. Now, let's talk about which one would make sense. X is greater than 20. Well, we just said I can't go over that $20, right? I can't spend $30, and that's what this is saying. What would be greater than 20? Well, $30 would, $21 would be greater than, $50 would be greater than. I can't spend any of those. All right, so a greater than symbol does not make sense for this inequality. But a less than does make sense. I could spend less than 20, right? I could spend $1, I could spend $15, all right? I have enough money for that. I could purchase something that costs $15. But I could also purchase something that would be equal to 20 as far as with tax and all that kind of stuff. If it came out to be exactly $20, I still have enough money. All right, so this one we would actually want to use the less than or equal to. But this is just an idea for you to understand why inequalities are important and why we have them. Because we actually use them a lot, or use the idea of them a lot in our daily life. All right, budgeting, things like that. I have this amount of money. I cannot spend more than this, okay? Or greater than. We have that for driving age, legal drinking age, things like that. You have to be greater than or equal to 16 to be able to drive or get a driver's license. You have to be greater than or equal to 21. If you're 21 years old or older, you can legally drink. All right, so these symbols are used a lot as far as conceptually. We know them, we use them. We know that we can't drink if we're under 21, but we don't necessarily write it this way. So that's why we're talking about inequalities, because this is how you write it for math. Okay, so at this point we're going to go ahead and start looking at some of our examples together, starting with problem number 1, and then we're actually going to be graphing them on a graph, on a number line, and talking about what it looks like in the math world instead of just for real life situations. For problem number 1, our inequality is x is greater than or equal to -3. Okay, so that means any number that's bigger than or the same as -3 is a solution for this inequality. That means there's tons of answers. Okay, anything bigger than -3. So -1, +3, 5, +7, +252. So that's another difference between inequalities and equations. If this was x equals -3, there's one answer. It's -3, and that's it. All right, with inequalities, you have many, many answers. Any number that's bigger than -3 makes this inequality true. So there's infinitely many answers, okay? 5,285. That would be an answer for this inequality because 5,285 is greater than or equal to -3. All right, so lots of possibilities here. So we actually are going to graph the answer for this inequality on a number line and have a visual representation of what those answers look like. All right, so we are going to start at -3, all right, because that's the number we're given. We'll start at -3, which is right here on our number line, and we're actually going to just put a dot there, okay, a nice filled in dot, because -3 is part of the solution for this inequality. It says equal to, all right, we've got that equal to bar. So -3 is greater than or equal to -3, all right, because of that equal to bar, this is a solution. Now, we just talked about any number bigger than -3 is also a solution. So we talked about how 0 would be a solution, 3 is a solution, 5, 7, 200, you know, going on and on and on. So anything on the right side of this dot is bigger than -3. All of these numbers are bigger than -3. So they're all solutions. They're all potential solutions. So you just draw a line, and then you put an arrow saying, hey, this keeps going. My number line doesn't, but my line does keep going in this direction forever and ever and ever. Those really big numbers, they still count. But because I can't draw a number line that big, I'm just going to put an arrow to show that this keeps on going. Okay? This would be the graph for this inequality. All right? -3 and anything bigger than -3 are all solutions for number 1. Now, let's take a look at number 2. For number 2, we have x is less than -1. And I want to write this draw this inequality on my graph. So let's think about it first. X is less than means smaller than -1. So what kind of numbers are smaller than -1? Well, here's my -1. If I move off to the right, I've got +3, I've got +5, 7, 6, 4. All of those, these are all positive numbers. All of them are bigger than -1, right? A positive amount is always bigger than a negative amount. So I'm not going to the right this time because these are all bigger. Off to the left is where the smaller numbers are. So let's start by drawing our point at -1. Now this time, I'm going to use an open dot at -1. Now the reason why I used a closed dot here is because -3 was a solution. We had that equal to bar. Over here, I don't have the equal to bar. -1 is not a solution for this inequality because -1 is not less than -1. Yes, that's true. They're not less than each other. They're equal to each other. So -1 doesn't work. But anything smaller than -1 does work, right? -3 is smaller. Negative 6 is smaller. Negative 255 is smaller. Anything off to the left side is smaller than negative 1. So I'm going to go ahead and make a nice line here with an arrow going like this. All of those numbers are smaller than negative 1. So they're included. Okay? Make sure you pay attention to whether it's an open dot or a closed dot. Okay? It's open when negative 1, in this case, when the number is not a solution. When there's not an equal to bar, it's nice and open. Okay? When there is the equal to bar, it should be closed. For problem number 3, our inequality is r is less than 2, or r is smaller than 2. Okay, so our first step is to figure out where our first point goes. All right, if it's 2, we go to 2 on our graph. Now, we need to know if it's going to be an open dot or a closed dot. All right, this is telling me that r has to be smaller than 2. It cannot be equal to. So if we're missing that equal to bar, it will be an open dot. So we will put an open dot at positive 2. Now, I want any number that's smaller than 2. Well, if I move off to the right, I've got 3, 4, 5, 6, 7. These are all numbers that are bigger than 2. I don't want bigger than 2, I want smaller than 2. Over to the left, I have 1, 0, and I get all my negative numbers. Negative numbers are smaller than positive numbers, so this is the direction I want to go. I want to go to the left. So I draw my arrow, my line, going off to the left-hand side. And remember, put that arrow at the end to show this is going on forever and ever, okay? It goes all the way down into the negative 300s, negative thousands, 10,000s, negative millions. All of those numbers are included because they're all less than 2. I just can't show them all. So I put an arrow to represent it keeps going. And this would be our graph for number 3. For problem number 4, our inequality is x is less than or equal to 1. So let's start with our first point. It has to be at 1, which is right here on my number line. And then I have to figure out if it's a filled in dot or an open dot. Well, this says x is less than or equal to 1. Well, that means that 1 can be a solution. So 1 is where we start, and this is going to be a closed in dot. Okay, filled in, because 1 is an answer. All right, it's only open when that number, like the 2 over here, was not a solution, because it's not equal to. But in this case, 1 is a solution, so we'll fill it in. Now it says less than or equal to. Okay, well, if I move off to the right, 2, 3, 4, 5, 6, 7, all of these are bigger than 1. I don't want bigger than, I want less than, smaller. Whereas if I move off to the left, I have 0 and all my negative numbers. Negative numbers are always smaller than positive numbers, so I must draw my line going off to the left-hand side. And that would be my graph for problem number 4. For problem number 5, our inequality is 6 is greater than n. Now this looks a little bit different because we've been used to seeing inequalities where the letter is on the left-hand side. So let's first start with our starting point on our inequality here, on our number line. We're starting with 6. That's the number that we're given. So I know that I need to put a point at 6. Now I have to determine if it's going to be open or if it's going to be closed. And we always determine that by whether or not it's equal to. If it's equal to, it's closed. If there is no equal to bar, it's open. In this case, we're given the greater than symbol. There is no equal to bar, so this is going to be an open point at 6. Now, here's where it gets a little bit tricky. This is saying that 6 is bigger than n. That confuses me. All right, I don't like seeing the letter on the right-hand side. I always like having my letter on the left. So I'm going to rewrite this inequality with n over here and 6 on the right side. Now I have to determine what my inequality is going to be in the middle. If I leave my inequality the same, this says that n is bigger than 6. Okay, if I think of a number that's bigger than 6, let's try 10. 10 is an easy number to work with. 10 is bigger than 6. That makes this true. Let's check it in our original inequality. 6 is greater than 10, or 6 is bigger than 10. That's not a true statement, okay? 6 is not bigger than 10. 6 is smaller than 10. So 10 does not work, which means my inequality sign here at the bottom is not correct. If 6 is bigger than n, then n cannot be bigger than 6. N must be smaller than or less than 6. Okay, if I try a number that's less than 6, like 1, let's try it here in the original inequality. 6 is bigger than 1. That's a true statement. All right, so if you decide to move the letter over to the left, which I recommend, I always do that so it's easier to graph, you must, see how I flipped the inequality sign? It was, the pointy part was at the end. The pointy part is still at the end over here, okay? It's open, the open area is towards the 6. It's open or it's eating the 6 down here. That means that these two mean the same thing, they're just written a different way. All right, so whenever you move your letter off to the left side, if it's on the right, move it to the left, you have to move your inequality with it, okay? So now n is smaller than 6. Well, numbers that are smaller than 6, we just said 1. All negative numbers are smaller than positive numbers, so I must be drawing a line off to the left side with an arrow. All the numbers that are smaller than 6. So once you rewrite it, it's much easier to graph. Let's try that concept again with number 6. Number 6, we have negative 5 is smaller than b. So first, we're going to put a point at negative 5, all right? I need to figure out if it's open or closed. So looking at my inequality, there is no equal to bar. Remember, if there's no equal to bar, it will be an open dot. If there is an equal to bar, it will be filled in. So I'm going to put an open dot at negative 5, right there. And now I'm going to rewrite my inequality because this is hard for me to figure out which way the line's going to go. So I'm going to have b on the left side, negative 5 on the right side. And I'm going to determine, okay, negative 5 is supposed to be smaller than b, which means that b must be bigger than the negative 5, okay? If negative 5 is smaller than b, then b is bigger than negative 5, okay? That's saying it in reverse, okay? If negative 5 is smaller, then b must be bigger, okay? So b is bigger than negative 5. Well, numbers that are bigger than negatives are positives. So all of my positive numbers must be bigger than negative 5. They're off to the right side. So I'm going to draw my line off to the right side with an arrow showing that this goes on forever and ever and ever. Just like that. So this would be our graph for number 6. For problem number 7, our inequality is 3 is less than or equal to n. So our first job is to go ahead and put a point at 3. So I have to figure out if it's going to be open or filled in. Remember, the equal to bar is what tells you if it's going to be an open dot or a closed dot. This says less than or equal to. If it's equal to, it is filled in. So I'm going to put a filled in dot at 3. Now from here I'm going to go ahead and rewrite this inequality so it makes a little more sense to me and I can actually draw my line. So the n will come first. The 3 will come after. Now I have to figure out what kind of inequality sign I need. This says that 3 is smaller than n. Well, if 3 is smaller than n, I always think about if something's smaller than me, I must be bigger than that something. So n must be bigger than or equal to 3. Well, numbers that are bigger, if here's my 3, I have 4, 5, 6, 7 going off to the right. Those numbers are all bigger than 3. So that means my line is going to go off to the right with an arrow showing that it goes on forever and ever. And that would be the graph for my inequality for number 7. For problem number 8, we have 1 is greater than or equal to n. My starting point is the 1, so I need to go ahead and put a point at 1. To determine if it's open or closed, look for the equal to bar. In this case, we do see an equal to bar, so that means it's going to be a closed dot. So I'm going to go to positive 1, I'm going to put a dot here, and I'm going to close it in. That means 1 is a solution for this inequality, because it's equal to. Now I'm going to rewrite it. N comes first, then the 1. This says 1 is bigger than N. Okay, well, if something is bigger than me, I must be smaller than it. Okay, think of people, height. All right, if someone's taller than me, I'm shorter than them. So, if 1 is bigger than N must be smaller than or equal to 1. Okay, well, here's my 1. If I move off to the right, I have 2, 3, 4, 5, 6, 7. Those numbers are all bigger than 1. I don't want bigger, I want smaller. So I must be going off to the left. Negative numbers are smaller than positive numbers, so I want to move off to the left with my arrow. So it looks something like this. And that would be our graph for problem number 8. At this time, go ahead and pause the video. Try problems numbers 9 and 10. Come back and check your work with mine. For problem number 9, the inequality is x is less than -4. The nice thing about number 9 is that the letter is already on the left-hand side, so that makes it easier for us to graph. I put my point at -4. I left it as an open point because there is no equal to bar. So -4 is not a solution, just anything smaller than -4. Now the smaller numbers are off to the left side, smaller negatives. Remember, bigger numbers like positives are off on the right, so I want my arrow to go off to the left side for number 9. And that should be your graph for problem number 9. For problem number 10, we have -1 is less than k. So our letter is on the right-hand side, which I don't like it to be there. So I went ahead and flipped my inequality. I put the k first and then the -1. If -1 is supposed to be smaller than k, then k must be bigger than the -1. Now I put an open dot at -1 because there is no equal to bar. Anytime you're missing that equal to bar, it's an open dot. And then I did a line going off to the right side because the right has the larger numbers, like +3 or +6. Those are both bigger than -1, so my line should go off to the right. And that's the end of our lesson on inequalities.